Watch the marked point on this stretched spring. A wave travels to the right, but the marked point does not travel with it. It oscillates about its equilibrium position and returns to where it started. The disturbance travels, but there is no net transport of material with the wave in this ideal model. This is a progressive or travelling wave. In a mechanical wave, particles oscillate about in equilibrium. In an electromagnetic wave, electric and magnetic fields oscillate instead. Here, wave speed is the speed at which the disturbance propagates, not the oscillatory speed of one particle. Freeze the wave at one instant. This displacement distance graph is a snapshot of the displacement at many positions. Displacement is measured from the equilibrium and can be positive or negative. Amplitude is the maximum magnitude of displacement measured from the equilibrium to a crest, not from trough to crest. The full height is 2a. Wavelength, lambda, is the shortest distance along the direction of the propagation between points in the same phase. Adjacent crests are an easy pair to use. The curve is not one particle's route, it records different particles at one instant. Now keep one point and watch it as time passes. The horizontal axis changes from distance to time. This displacement time graph is one particle's history. The time taken for the motion to repeat is the period t. Frequency f is the number of oscillations each second, so f equals 1 over t. The two graphs can look identical, but their horizontal units decide what they show. A distance graph gives wavelength, a time graph gives period. By itself, one graph does not directly give both. Return to our wave. The distance graph repeats every 0.80 meters, so that is the wavelength. The time graph repeats every 0.20 seconds, so the frequency is 1 divided by 0.20, 5.0 Hz. In one period, the wave advances by one wavelength, so its speed is lambda over t, which is f lambda. Wave speed may be written as c or v, the equation is unchanged. 5.0 multiplied by 0.80 gives 4.0 meters per second, the wave speed, not the marked point's vertical speed. On an oscilloscope, horizontal divisions across one cycle multiplied by the time base give t. Then f equals 1 over t. Vertical divisions from the zero voltage line to peak multiplied by the y gain give the signal amplitude. The full peak-to-peak height is twice the amplitude. Phase is the stage reached within a cycle. Phase difference compares two positions on the same wave at one instant. These points are 0.20 meters apart along the direction of propagation, 1/4 of the wavelength. Their phase difference has magnitude 1/4 of a cycle, which is 90 degrees or pi over 2 radians. For points on one progressive wave, phase difference equals 2 pi times separation divided by wavelength. One wavelength gives 2 pi, so the points are in phase. Half of a wavelength gives pi, so they would be in antiphase. Equal displacement does not prove equal phase. A single snapshot can also not show the direction of travel. That needs a later snapshot or information about the particle motion. A progressive wave transfers energy. Its intensity is power per unit area perpendicular to the energy flow. For the same type of wave, with frequency, medium, and other conditions unchanged, the intensity is proportional to the amplitude squared. Double the amplitude and the intensity becomes 4 times as large, not twice as large. Read the horizontal axis first. Distance gives wavelength, time gives period. Use f equals to 1 over t and c equals f lambda. Treat phase as a fraction of a cycle and keep wave speed separate from particle motion. Next lesson we will compare transverse and longitudinal waves and then use polarisation as evidence that a wave is in fact transverse.